Hello everyone, welcome to our webinar on monitoring green roof performance with weather stations to be presented by John Buck of Civil and Environmental Consultants. My name is Paul Gannett and I'm Product Marketing Manager here at Onset for our environmental products. I am going to give a brief introduction and then I am going to turn this over to John. We will have time at the end for your questions. You can send us questions at any time by typing them into the GoToWebinar control panel. We will address as many of these as we can at the end and follow up by email on the others. We are recording this webinar and we will send you a link to the recording afterwards so you can refer back to it in the future. First, a little about Onset for those of you who don't know us. We are the company that makes the HOBO data loggers, which are used around the world for a wide range of applications with over 2.5 million of them deployed. Our markets can be grouped into environmental monitoring and energy management. Within environmental monitoring, we offer loggers for monitoring outdoor and underwater environments. Everything we do is related to conservation, with our loggers being used to better understand the impacts of global warming and development and coming up with better ways to protect our environment and save energy. I want to briefly mention the HOBO stations, which are widely used for monitoring green roof performance. The HOBO stations can be used to monitor weather conditions, microclimates, and soil conditions, and they can also be used to activate irrigation systems. HOBO systems are scalable to meet your site and budget requirements, with choices ranging from our inexpensive 4-channel loggers to full web-enabled 15-channel systems, and there are a wide range of environmental sensors to choose from. The sensors are plug-and-play for easy system configuration. Our web-enabled systems provide easy viewing of site conditions and make it easy to share results with others through the public access feature. And all of this can be done without having to be a programmer. In John's presentation, you will see some great examples of how HOBO systems can be configured and the kind of results you can achieve. Now, I'd like to introduce our presenter. We are very happy to have with us John Buck, Project Manager with Civil and Environmental Consultants. John has degrees in biology and agronomy. He has extensive experience related to soil and plant relationships, including revegetation of disturbed lands, invasive plant management, phytoremediation, and green roofs. Today, John will be sharing with us his green roof design and research experience from several of the projects that he has managed. So, with that brief introduction, here is John.
Hi, everybody. Thank you in advance for your interest. I want to remind you that Onset is going to be posting this on their website, so don't worry about reading every word. I'm going to move fairly quickly along. So we'll get going. I've been working with civil and environmental consultants now for about 20 years, and it's a very diverse company, over 500 employees, about 250 in our home office in Pittsburgh. I'm really very lucky to have the colleagues I do and the projects and clients that we do. Moving along, I will, let's see, grasping with the controls here. I'm going to quickly review the agenda for the talk and then we'll move along. First, we'll talk a little bit about why are we building green roofs, and then why are we monitoring them and monitoring other green infrastructure for that matter. Some of the key tools with monitoring green roofs and green infrastructure. Drill down in particular into soil volumetric water content monitoring. And we'll talk about minimal and more enhanced monitoring configurations. Some installation nuts and bolts to consider, and we'll talk about web-enabled data collection and remote feedback, which is a great asset of the Onset loggers. And we'll talk a bit about opportunities to actively control systems that you're monitoring, not just the monitoring system, but say irrigation while you're doing that monitoring using logger relays. And we'll touch on hybridized green infrastructure ideas, and then finally we'll take questions. So why green roofs? The primary driver for green roofs is stormwater quantity and intensity management. Taking the quantity down, taking the intensity down. And the goal of that is to reduce combined sewage overflows, or CSOs, and also to reduce flooding potential from impervious surfaces like roofs. A very important side benefit is temperature moderation, and that improves building operating efficiency and also reduces the temperatures in the neighborhood and the planet ultimately by reducing the urban heat island effect. Then finally, aesthetics and green space. You can be creating a park on your own roof. So why monitor green roofs? The main reason is to reduce uncertainties, speed adoption of green infrastructure by demonstrating their benefits. And in the process of monitoring, you can go about improving designs, optimizing designs, finding those sweet spots where you're getting the most bang for your buck. This photo was taken last week at the Allegheny County office building in Pittsburgh, Pennsylvania. In the background is the former county jail. See a weather station on the right, and on the left we have a very small green roof microcosm. And when I say microcosm, a microcosm is in this case a miniature of the green roof under study. Essentially, in this case, we've taken a slice of the green roof, we've elevated it, and that's enabled us to put plumbing underneath to capture drainage from the soil layer and measure it in the underlying tipping bucket rain gauge, a little white cylinder under the microcosm. So what Allegheny County did is they're trying to set an example for the rest of the county, get people comfortable with green roofs, and they thought they would start with themselves. They built a green roof on half of their office building. The other half they left as it was, a modified bitumen roof, as a control. And we put in a network of about 100 sensors on the control and on the green roof side, and in the office space below, because we wanted to get at some of the heat flux questions. We had to measure some temperatures below the roof deck. We're getting our most quantitative drainage information from these microcosms, and we're looking at the variable of soil thickness on green roof hydrologic performance. So we have an extensive green roof that's 4 inches thick, a semi-intensive, which is 6.5 inches thick, and an intensive green roof that has a 10-inch thickness of soil. And you'll see we also have a little control microcosm. We're just measuring temperature there. So the idea is, if soil thickness is sort of like how big, how dry a sponge you're putting over the roof. So we would expect with our extensive thin soil roofs that we have less absorbency, more drainage or net runoff, and then thicker soils you would expect to perform better hydrologically, but they weigh more, they cost more. Paul, could you advance that, please? Having a little delay at my end here. Okay, sorry. Just a quick view of the roof 1 month after planting. You can see these are small plugs. And about a year later, it was very well grown in. You see H and L, those are high and low landscape positions, and in those positions we put nests of 3 soil moisture sensors, 3 soil temperature sensors, just as we also had in the drainage measurement microcosms. And the idea was to do some testing in the wild as well as in these microcosms. So the idea with the microcosms being all put together, we could get all of them into the same microclimate. Get a closer view of the construction of the microcosms. This one was at the Rockwell Automation headquarters in Milwaukee. We're measuring both roof drainage and roof runoff, roof surface runoff. And if you have to make any choices about what you monitor, what you don't monitor, I would say don't bother with runoff over the surface of the soil. We got essentially nil runoff, but we did get roof drainage to the soil depending on the weather conditions and the soil antecedent moisture contents. So we ended up collecting a lot of data, and it gets posted automatically to Onset's HOBO link website, and we wanted to do some interpretive statistics, so our web programmers at CEC automatically pulled off the data from the Onset server, put it into their own program, and generated some interpretive graphics. I would get calls from people, well, how's the roof doing? I have to go through manual calculations, and this way it self-updates every several hours. Credit Brandy Bukovic at CEC for that work. You might want to look at this website. So in looking at the performance of the green roof microcosms and the amount of stormwater attenuation over a year, we identified a design sweet spot of about 6.5 soil thickness. The 10-inch thickness, as you'd expect, did better, but not that much better. So in the 4-inch treatment, substantially less effective at retaining stormwater. One thing I would like to do, and we have done in concept and on a demo basis, is monitor and know ahead of a storm how much green roof soil moisture storage we have. How absorbent is that roof? So we know before the storm whether we can absorb, say, the first 0.3 of an inch or the next 0.7 of an inch. To do that, we made observations of soil moisture as a function of rainfall, and then the maximum water retention of soils at 3 depths, 1 inch, 3 inch, and 5 inches in this example. And we looked at what that maximum water retention was for each soil depth interval. And by comparing the difference between where we are and what the maximum water retention of that soil is, we can calculate the available absorbency of that soil. Now, it's important to note that the drainage layers also have some absorbency, as do succulent plants like sedum, which can be quite significant. So this will tend to be an underestimate of green roof water storage capacity. So when we roll that up, next slide, let's see. Stand by a moment. Paul, could you advance that, please? Okay, what we see here, well, let's advance that again to slide 24. Okay, 24. You see same rainstorm, and we have our calculated remaining soil absorbency in the green plot, rainfall in the blue, and again, no runoff. These rainstorms were low enough intensity that we never overwhelmed the soil's absorbency. Paul, can you advance to slide 25? In wetter weather, with the soils nearly saturated, you can see that we did develop some green roof runoff after a delay period, and there was a net reduction in roof runoff. So when soils are very wet, you get less absorbency, as you would expect, and but you do have a delay in that green roof runoff, which has value to CSO management, as well as a reduction in overall runoff. So these are the things we can be quantifying on these monitored green roofs. Let's go to slide 26, please. On the temperature side, in the heat of the sun in the summertime, we're seeing as much as 60-degree difference in roof surface temperature between the green roof and the control roof. Same building construction, same sun exposure. This is good for energy efficiency. It's also good for the longevity of the roof. Roofs get beat up by expansion and contraction. Generally, green roofs can be expected to last 2 to 4 times as long as a exposed roof. Next slide. Taking that heat transfer theme to a more quantitative level, students at Carnegie Mellon University took our data, and they were able to get into the HOBO website and download it themselves. And they compared the heat flux between the green roof and the not green roof through the warm and the cool months. Next slide. What they found was that in the warm weather, when air conditioning was being used, the green roof was reducing heat gain in the building 75%, whereas in the winter time, the heating season, they had an 8.2% reduction in heat loss. During the warm months, we expect that evaporative cooling played a big role beyond insulation effects in that big performance difference. I should point out that between 2009, which was pre-green roof, and 2010, the county office building spent $90,000 less after the green roof in 2010 and 2009. This despite being a warmer year than the pre-green roof condition. So, next slide. Month-by-month view from Wang and Becker. Next slide. So we'll talk a bit about tools in the monitoring system. On the left, we've got these sensors that would be attached to a data logger associated with a weather station. On the right, and particularly the 3 underlined soil moisture, soil temperature, and drainage, are monitored parameters that would be unique to a green roof monitoring system. And these data loggers can also measure other things, water depth, voltage, millivolts, whatever you desire. Next slide. Key to monitoring green roofs is knowing where the water is going. And we're using dielectric soil moisture sensors made by Decagon and sold by Onset at the Allegheny County office building and other locations, and also soil temperature sensors. Next slide. Key thing about soil volumetric water content sensors is they rely on the dielectric properties of liquid water. So if soils are frozen, there's going to be apparent lack of water. So that's why you need to be monitoring temperature at the same time you're monitoring volumetric water content to make that interpretation valid in the wintertime. They're very rugged, affordable, and you have to be mindful of the model-specific volume of influence that these sensors have. Next slide. By way of contrast, these are two Decagon sensors that Onset distributes. One is the Decagon EC5, which looks at a very small volume of soil influence, only about 0.3 of a liter. Imagine orienting the sensor like were the size and shape of a soda can. That's the volume of soil that you're interrogating. That's very good for resolving differences over short distances, as in thin green roof soils. There's also the Decagon 10HS, which is same principle but it's longer, and it interrogates 1 liter of soil. So imagine a 1 liter water bottle. And you can orient this horizontally for a narrow depth interval or vertically for a broad depth interval. For green roof soils, I go with the Decagon EC5. Next slide. So another key tool are tipping bucket rain gauges, and not for just measuring rain, but for measuring water flow, literally 1 teaspoon at a time. And the neat thing about these tipping bucket rain gauges is that every payment of water is time-stamped. And we're adapting these with plumbing to measure flow out of the green roof soils in microcosms or small pan lysimeters. So tipping bucket rain gauge is essentially a funnel directing water into a self-emptying pivot bucket with a counter on it. Next slide. And this is the funnel removed on the left and the tipping bucket mechanism on the right. Next slide. So if you're looking at minimum and enhanced configurations for green roof monitoring, at a minimum you need a rain gauge because rain varies greatly over short distances. Soil volumetric water content sensor, I would go with at least 2. Soil temperature sensors, again, I'd go with at least 2. And then if you're going to be directly measuring drainage with pan lysimeter or microcosm, you need a second rain gauge to do that. So the advanced system would be, all the above plus other weather parameters like air temperature and relative humidity, solar radiation, and wind speed. That would allow you to model evapotranspiration rates and temperature below, above, and within the roof layers. Next slide. So back to that microcosm on the roof of the Allegheny County office building. This is a very simple demonstration. It all is within the capacity of one data logger, and it generates very quantitative data on drainage and soil moisture, temperature, as well as weather. Next slide, please. So talk a little bit about an alternative to this microcosm that, is essentially a slab of soil lifted up on a table that you saw before. That's an in-ground pan lysimeter. Next slide, please. This is the Phipps Conservatory Center for Sustainable Landscapes in Pittsburgh. It's the greenest conservatory in the world. We're monitoring green infrastructure, rain gardens, and also green roof. Next slide. And this time we set up the drainage capture pretty much at ground level, boosting a laundry room sink with the top cut down, and then plumbing into it, and then sending that plumbing into a tipping bucket rain gauge protected inside that bucket with a lid on it. Next slide. So here's our pan lysimeter with the under drain on the left, and then backfilled with soil on the right. Having the edges of the pan lysimeter rise all the way to the surface is highly desirable. Avoids the phenomenon of soil-water convergence or divergence. Next slide. Just a little more on the construction sequence. You see the wires leading out from the sensors over that pan lysimeter. Next slide. And we've been monitoring this since July. We've had a lot of rain events and only 3 that have produced any net drainage, and that net drainage was a scant fraction of the rainfall that came down on the roof. So, next slide. Here's a substantial rainstorm from mid-September. We had about 48 millimeters of rain, about 2 inches of rain, and 94% of the storm water was retained. That's despite the fact that the plants have just barely grown in on this green roof. Next slide. So if you are going to quantify drainage from green roofs, I encourage you to do that. Cautions. Pan lysimeters and sort of the green buffer zone around them have to have free vertical drainage. If there's any backup inside or outside the pan lysimeter, you're going to distort the apparent drainage rate. And you can avoid that if pan lysimeter boundaries up to or very near the surface. Make sure, if you're measuring flow with a rain gauge or with any other device, that you have adequate filtration to keep dirt from blocking them up, and adequate maintenance access. Next slide. Some nuts and bolts, some installation considerations. Think about how the green roof is going to be constructed. Work with the contractors and with others involved to see how you can, stay out of each other's way. If you have a slope with significant relief, I would try to get some monitoring points at high and low elevations, or at least at the high locations. Be aware of sensor wire length limitations. There may be limitations on how far you can run a wire, and by all means protect the wire and conduit. You're going to have people planting, placing soil, a lot of opportunities for wires to get cut. And you want to do everything you can to protect the roof membrane and make sure you don't damage its integrity or the warranty in setting up your monitoring system. Obviously, you're not going to put screws into the roof deck to hold down your equipment, but you can, say, use ballast to hold it down. Consider roof access. Keep it easy to collect data from the loggers, and I would urge you to consider some, cellular or Wi-Fi wireless telemetry, so you can get the data without actually visiting the roof. Finally, don't forget to have adequate time and money budgeted to maintenance of the monitoring system. Next slide. So just a construction photo. We're using 1.5-inch conduit to run our sensor wires and protect them. And then during the construction process, we tucked those wires into the pipes so that no one was tripping over them or otherwise damaging them. Next slide. If at all possible, establish some web access to your data. It saves you time, increases data security. You're getting your data backed up on a server, not just the memory chip of the logger. Also allows you to remotely troubleshoot, program, and relaunch loggers if you need to, and to share the data with others. With the Onset loggers, they've got a web page where you can establish alert criteria and also establish thresholds for actuating a relay to, say, control irrigation equipment or other gear of interest. Next slide, please. Just an example dashboard. You can see this one logger is having a communication problem. Their Wi-Fi was down. So I got an email message telling me that was a problem. I was able to look into it and call the IT department involved. Next slide. So if you have a logger that has a programmable relay, you can program that relay to open or close based on your sensor readings, and use that to precisely manage irrigation. Could be used to manage pumping out of, say, a rainwater collection cistern, valve opening or closing, whatever it is you would like to do. Next slide, please. An example of a relay-controlled system, Scalo Solar project in Pittsburgh. They're demonstrating several flavors of photovoltaic generation, and one of those flavors is to put a green roof around and between the solar panels. And the consequence of these black solar panels being near the vegetation is that it gets very hot, and we want to irrigate this thin, hot green roof to keep it alive, and but we don't want to over-irrigate it. So what we did was we took our soil moisture sensor, we established moisture threshold and also temperature threshold. So irrigation would only come on if it was too dry or too hot for the plants. Next slide, please. So this is an example dashboard. You can look up at any time what the relay state is, if it's open or closed, what the sensor readings are at the moment, and you can also download historical records. Next slide, please. So in the case of the Scalo Solar project, I would say that probably probably 1/3 the irrigation that would have been applied by the regular irrigation schedule was actually applied because the data logger and its sensors were overriding the irrigation controller 2/3 of the time. So there were very big irrigation savings. And slide. In the Onset HOBOware or HOBO link interface, as an owner, you can look up and see, when the relay was on, when it was off, what the thresholds were which triggered that relay, and in doing so, you can very quantitatively document, how many irrigation cycles you interrupted and when, and quantify the savings. So, and you can also have the system send you text messages or email messages whenever these thresholds are met. Next slide. Another example of green roof monitoring and irrigation control with the monitoring system. This is the David L. Lawrence Convention Center in Pittsburgh, LEED Platinum Convention Center, first of its kind. The system has a sedum green roof on the left and a more wildflower based green roof on the right. Next slide. So key components are the data logger. This is a Onset U30. Soil moisture and temperature sensors and the rain gauge, which are reporting to the data logger. And then the relay circuit, which is just interrupting the irrigation controller when certain conditions are met. Next slide, please. So you see center bottom, the data logger, the solar panel that keeps the battery charged, and I should point out that 1.5" PVC is a great medium for making stands for these loggers. Next slide. And next slide. Inside the guts of the logger, there's a simple 2-lead connection for the relay. I'm no electrical whiz, but I could figure it out. It's very manageable system. Next slide, please. So there are opportunities to hybridize green infrastructure. We can often have budgets or building roof loading limitations that keep you from building a big, thick green roof that can store a lot of water. So the workaround would be to use a thinner, lighter green roof combined with irrigation and runoff storage. So you can be collecting runoff from when the roof's absorbent capacity is exceeded. Collect that runoff in tanks at ground level. And then you can use the logger relay to trigger automatic irrigation from those cisterns when the conditions dry down. And by irrigating, you will be able to have a more robust and more diverse plant community and also increase evaporative cooling. So you have the structural guts on the building, use a thin green roof by all means in consultation with an architect and structural engineer, and store the water somewhere else in a cistern. Next slide. So some closing comments. I hope the takeaway is that data loggers and sensors and green roofs can be used to demonstrate stormwater green infrastructure performance, demonstrate improved building energy balance, that is, less heat loss in the winter, less cooling needs in the summer, and help you actively intervene in irrigation and thereby reduce water use. Scalo Solar, I think we cut our water use to 1/3 of what it would have been. And help make the environmental case for green roofs as well as the economic case for green roofs. Next slide. So I'm finished presenting, and I believe Paul is. And if you have any questions, I'd be happy to answer them. Next slide, please.
Sorry, we're just looking through the questions now. So let me expand that out. Oh yeah, lots of questions. Are you, John, are you able to see the questions on your end?
Let me see if I can expand the window.
Yeah, if not, I can read some of the good ones to you.
Yeah, why don't you read them to me?
Yeah. Yeah, okay, we'll just start out with this one. Your data suggests that perhaps a better sweet spot is between 4 and 6.5 inches. Are these values based on plant root system requirements, or are you pursuing gathering data for, say, 5 inches? Want to expand on that?
Yeah, Edwin, when I spoke of a sweet spot, I meant sweet spot in terms of reducing stormwater drainage from the roof. So the 6.5-inch thick soil system retained a whole lot more stormwater and would-be runoff than did, say, the 4-inch, but not that much less than the substantially more expensive 10-inch thick growing medium. So sweet spot is more about water storage capacity of the soils and avoided drainage. The root systems, from what we could see, were penetrating the full depth of whatever soil we presented the plants with. There were lots and lots of fine fibrous roots right at the soil drainage layer interface. So plants will exploit what you give them, especially if there's adequate aeration and drainage, and there is in this case.
There's another question here. Do we really need to measure runoff, or is a rainfall measurement sufficient? Can't we just use green roof curve numbers, perhaps modified by soil holding capacity? Thoughts on that?
You can. I don't think you need, when we look at runoff, we should break that down a little bit. Water is leaving green roofs mainly through drainage at the bottom into the drainage layer, not runoff across the surface. So if we combine those two, that would be kind of net runoff. It is far more satisfying to directly measure drainage / runoff from the green roof than to rely on curve numbers. Now, anything you can do to reduce the number of assumptions is going to, increase confidence in the designers that have to seal the drawings or skeptical reviewers. So you can use curve numbers, and I think if you modify them with some real actual measurements of soil water retention, that would be a much stronger case.
Yeah, thanks, John. There's another question here on how would you approach monitoring on a larger scale? Any thoughts on that?
Yeah, one thing that would be very desirable would be to measure everything that goes down the drain and put some sort of flow monitoring device in the roof drains themselves, and that way you're not extrapolating from small microcosms to the entire roof. We have considered that on a couple of projects, and folks have gotten nervous about the potential for backing up around the storm drains. So we've used small microcosms and then scale-ups based on surface area relationships. But if you can work in a direct measurement of the entire drain flow, that would be very, very desirable. As long as you can do it without causing a backup at the roof drain.
Yeah, to add to that, there's something called a tipper flow measuring device, which is basically just like the tipping bucket mechanism within our rain gauges, but on a much larger scale, so they can measure a large flow rate of water.
Yeah, I think with new building construction, I think you could accommodate those measuring devices easier than some of the existing buildings that I've done work in.
Yeah, I guess actually I see another question here as a follow-on to that is, does Onset have any plans to develop a larger scale tipping bucket? And yeah, I guess it's not right now, but we don't have one in active development right now, but that's certainly, as we look forward to the future, that's something we may consider, so stay tuned.
So if I could pipe in, I would say, one approach I've seen with larger roof watersheds is to use a very shallow flume to back up a relatively thin film of water and then measure with great precision the depth of the water behind that flume. You could do that, and where I saw it done was at Carnegie Mellon Hammerschlag Hall. They used a laser, or I think it was a laser-based proximity measurement to get at the water depth. It worked. It was a little challenged by leaf debris and that sort of stuff that could foul the flume. Another option, if you can get the plumbing to work, is to use some sort of V-notch weir and high precision depth measurement in the pooled side of the weir.
Yeah.
And there is a way that you can correlate submerged depth of these dielectric soil moisture sensors in a vertical orientation to water depth. I've done that, and you can get some very nice correlations. So that's an option, if you don't want to use a pressure transducer, say, for depth. You could modify a soil volumetric water content sensor.
All right, so a few good options. I see a question here on how fast does evapotranspiration remove moisture from the soil, and what are the important parameters? I guess you want to talk a little bit about that, John?
Yeah, I can't give you a great number right now without rifling through some data, but in ballpark numbers, say around Pennsylvania, you could expect to have evapotranspiration rates in the neighborhood of an inch a week. But it really depends on light intensity, wind speed, relative humidity, and the size and type of the plants involved. And a lot of green roofs are planted with sedum, which are essentially, alpine plants with cactus-like metabolism. They don't lose water as quickly as as more conventional plants like grasses. So it depends a lot on the plant type planted. Now the very interesting thing about these succulent plants like sedum is that they can essentially shrink like raisins when they're losing water and things are getting dry, and then when you get a burst of rainfall, it's not just the soil sopping up water. The plant vascular tissues themselves can absorb about 10 millimeters of water. So soil-based estimates of water retention are conservative in that situation because the plants can themselves absorb a lot of water.
Yeah, good. And I guess you showed in one of your deployments, you can equip a weather station with those sensors necessary: wind speed, temp RH, a light intensity. You can have a weather station with those sensors installed, so you can get the parameters needed to calculate evapotranspiration with a proper crop coefficient.
Exactly right, and yeah, that's where having a complete weather station makes a big difference. You have the ability to calculate ET, and then you can compare it to actual water loss from your soil water content sensor measurements. Rob Burgage at Penn State Center for Green Roof Research has done some of that work with sedum and some of the other common green roof plants. He could probably help you with some crop coefficients more appropriate to those succulent plants.
Yeah, good. Here's another question that came in a little bit ago: is can you separately measure the energy savings from the soil heat capacity versus evapotranspiration? Any thoughts on that?
It's not my area of strength, but I think there's a lot that could be done with those data. I mean, you could look at the energy associated with the evaporative loss of the amount of water that you are monitoring and compare that to the heat flux that you're calculating from temperature differences across the ceiling, roof deck, soil, profile. So if you have that array of temperature sensors, you can collect or you can calculate heat flux, and if you've got soil moisture sensors, you can calculate water loss or measure water loss, and then explore that relationship.
You mentioned heat flux. There was a question on that as well. Does Onset have a heat flux sensor? And the answer on it is we don't have a heat flux sensor. How you'd have to solve that is with multiple temperature sensors on either side of a point of interest.
Yeah, I would pipe in that Carnegie Mellon University at their Hammerschlag Hall green roof did a lot of monitoring there, and they did have a heat flux sensor, but they had some reliability issues with it. And in a way, I think it's probably more instructive to have individual temperature measurements and in a teaching setting like that, and actually labor through the calculations, which can be automated. Key thing is knowing the thicknesses of all the roof components and then what their insulation values are, as well as those differential temperatures.
Yeah, good point. All right. Well, I'm thinking now might be a good time to wrap things up here. So got a couple more slides just to kind of to tell you where to go next, or where some resources you have available. Let's see if we can, yep, here we go. As you saw in the previous slide, John had included his contact information for additional information relative to green roofs. You can also contact us here at Onset for questions related to this webinar. You're welcome to contact me, and I'll try to get you the information you need. If you need help configuring a system or ordering a system, you can contact our application specialist. And if you have a system already and you need some help getting it going, you can contact our technical support group. As I mentioned earlier, we'll send you an email with a link to this webinar. We've been recording this, so you can refer back to that. If you missed any of the contact information slides, you can view them there. And also remember that the Onset website includes a wealth of information, including detailed information on our green roof monitoring systems, as well as white papers, application notes, and recordings of other webinars. Well, that wraps things up. I would like to say a special thank you to John for sharing your insights with us today, and to all of you who have joined us today. Thanks for attending.
Thanks for your